Hi, I'm Andrew. Thank you to the organizers for inviting me here to talk about basically how we can use gravitational waves to probe dark matter. So it's quite a big or broad topic, so I'm basically going to focus on particular results that we've just actually released a couple days ago of using gravitational wave interferometers kind of as particle physics laboratories to probe the direct interaction of dark matter with stellar model particles in the interferometers. So the details are in this paper. I don't know if this is a laser pointer, but anyway, yeah, the details are in this paper. But so yeah, I will talk to you about this paper. So basically, I'll give you some background about what kind of signals that we're looking at, and as well as I'll talk to you about the types of ultralight dark matter signals, and then talk to you about how the search that we've done using O4A, LIGO, Virgo, and Kagra data, and the constraints that we've obtained, and then some conclusions and prospects. So as the first speaker of the session has told us, basically we don't know a lot about dark matter, although we do know that it exists. It can span many orders of magnitude. The speaker focused a lot on WIMPs and other kind of this fermionic dark matter, but for this talk, I will focus on ultralight dark matter, which is roughly speaking around 10 to the minus 22 to kilo EVs, but I'll be focusing mostly on the 10 to the minus 14, 10 to the minus 12 EV range. And as the first speaker has said, basically we have so many models and we have no guarantee that any of them are right. And we often don't have any lower bounds on what the coupling of dark matter to the stellar model could be, if there even is a coupling. And so it's a very challenging problem. And so we just have to basically try to design experiments or data analysis techniques that are basically independent of the kind of model of dark matter, but yet allow us to then constrain multiple types of dark matter if possible. And with gravitational wave interferometers, we can actually do that. And so let me just give you some context. So we all know that what LIGO, Virgo, and Kagra were designed to do, which was to detect gravitational waves. But the fact that they are such that they measure positions of mirrors very, very precisely means that they can also be used for any kind of experiment in which you want to see what the impact is of something on moving the mirrors. And in this case, we want to understand if dark matter can interact in some way with the interferometer, pushing and pulling pulling the mirrors, or any other part of the interferometer, which will give off some kind of observable signal. And so the picture is that these detectors are sitting in some like ether of dark matter that's flowing through the detectors. And as the dark matter flows through the detectors, it's at some velocity given by the virial velocity of dark matter. This will, if they're interacting with some stellar model particles, they will shift the mirrors. And in principle, they will do this in the same way in all of the Earth-bound detectors, because the dark matter is ultralight and the coherence length of the dark matter particle exceeds that of the detection separation. So we expect correlated signals throughout the detector and on Earth. And so roughly speaking, we are on the ground, we are sensitive to between 10 and 2000 hertz. This means that we're sensitive to an ultralight dark matter range of 10 to the minus 14 to 10 to the minus 12 EVs. And so if there's any way that you can think of that can cause ultralight dark matter to interact with the interferometers and cause some movements of the mirrors or some other components, we can in principle search for it. You can think about it as almost like a source of correlated noise that's going to be in all the detectors, except the noise is actually a dark matter particle that's interacting with the interferometers. So just to give some more quantitative aspects of this. So as I mentioned before, the coherence length of dark matter is expected to be much larger than the separation between Earth-bound detectors, leading to correlated signals. And that's because the occupation number of ultralight dark matter particles in any given region of space is huge, given by this equation up there. But the finite coherence length of the dark matter particles also implies a finite coherence time. And that finite coherence time is given by the equation at the bottom of the slide. And you can see that the coherence time is on the order of 10,000 seconds, depending on the mass of the dark matter particle. And this implies that the signal is going to be monochromatic within this coherence time, but it will have stochastic frequency fluctuations on the order of the virial velocity squared if you observe for longer than this time. And this basically means that we're looking for a signal that's narrowband, so almost at the same frequency, with order millihertz variations in the frequency when you observe for longer than 10,000 seconds. And so we're looking for something that's monochromatic and everlasting. And so this means that the kinds of techniques that we use to search for neutron stars with bumps on them that we heard a little bit about, so these continuous waves, we can apply these continuous wave techniques to look for ultralight dark matter that interacts with the interferometer. And in fact, a lot of continuous wave techniques can be used to search for dark matter because whether it's in the form of primordial black holes or whether it's in the form of particle dark matter. So now I'll talk about the types of dark matter and what their observable signatures would be on the interferometers. So there's basically three that we consider in this work. One is a scalar particle, like a dilaton. It can essentially expand and contract the mirrors by interacting with the electrons and photons in and around them, which is spin 0. And then we consider dark photon dark matter, which is spin 1. This interacts with baryons or baryon minus lepton number, and it will accelerate the mirrors. And then we consider tensor dark matter spin 2, which is actually very similar to a gravitational wave. It modifies gravity in some way. It perturbs the space-time around the mirrors. So just to put this all in some pictures, the scalar dark matter particle, what it will do is it will couple to the electron and photon fields, and it will cause the sizes of objects to oscillate in time at a frequency that's fixed by the dark matter mass. And in particular, it will cause oscillations of the beam splitter, and it will cause oscillations of the end test masses in the interferometers. And so when you have these oscillations of the size of the mirrors or the beam splitter, this means that light will traverse different paths along the surface of the beam splitter. And of course, the differences in the thicknesses of the mirrors implies that this oscillation of the size of the mirrors will also cause a difference in the path length of light as it moves up and down the interferometer arms. And so we can essentially, this causes the differential strain that we need in order to actually try to detect this kind of dark matter. Then we consider dark photon dark matter, which essentially couples to baryons, so protons and or neutrons. And the idea here is that since the interferometer is sitting in this field of dark matter, and each of the mirrors is in a different place with respect to the incoming dark matter field, they will experience different realizations of the dark matter field, causing them to oscillate slightly different amounts. And that slightly different amounts of oscillation means that the path lengths of the light down each of the arms is different. And that gives rise to the differential strain. That's one of the effects. And the second effect is that because it takes the light a finite amount of time to go up and down the interferometer arms, the mirrors will have moved in that time in response to the dark matter field. And so you get an additional enhancement of the signal because of this so-called finite light travel time effect, which is not really present for the scalar or the tensor case. And for tensor bosons, there's not too much to say about them other than that they are a tensor perturbation like a gravitational wave, and this is some kind of like IUCAA fifth force modification of the gravitational potential, and this causes a signal very analogous to gravitational waves, and that it stretches and squeezes the space-time around the mirrors. So just another picture to show you what the signal really looks like. Here I've shown a plot of the strain versus time on the left and the Fourier transform of that plot on the right. And so you can see that, and this is an injected simulated dark matter signal without any noise. And so you can see that the signal is concentrated around a few millihertz in the frequency domain, but it has some finite width, as you can see this jaggedy structure. And this comes from the fact that you've taken a Fourier transform that exceeds the coherence time of the dark matter signal. So the signal is not monochromatic within this is 1 day of data. So the signal is not monochromatic within the 1 day of data that you've used for your FFT. And so this implies that we can think of how to analyze and look for these kind of signals, in that we should restrict the FFT length of the coherence time of our analysis to match the coherence time of the dark matter signal. In that way, when we do that, the plot on the right-hand side here, the power spectrum will be peaked at one frequency, and we will not lose any kind of signal-to-noise ratio because of this splitting in the frequency domain that arises from the observation time being longer than the coherence time of the signal. So this naturally gives rise to these semi-coherent, these non-match filtering based techniques to look for this kind of interaction. So now I'll talk about the O4A search that we've done. So there's 3 methods. I won't go into detail with these 3 methods, but essentially what they do is they either look for cross power, cross correlation between different instruments, or they build these time frequency maps and they look essentially for correlated power they analyze the data separately and they look for coincidences between any kind of recovered candidates that you have from each detector. And so in this particular picture, I've shown a time frequency map with an injected dark matter signal. And essentially, as I explained to you before, the signal is excessively monochromatic when you match your FFT length to your signal coherence time. And you can do this as a function of frequency every 1 hertz or so, which is what we do. And so that means you're looking for just a line in the time frequency plane. And so you can just make a histogram or sum the power along each of these frequency bins. And you get some kind of histogram, which you see on the right-hand plot here, where the peak is at the frequency of the signal. And so the methods, not the cross-correlation method, but the 2 other methods, and they're used in the search, they basically do this. One does it every hertz, matching the FFT length to the signal coherence time, and the other method does it every logarithmic frequency bin. So now the results, we didn't find dark matter. We did find some interesting candidates, but we threw them out because they were inconsistent. They were not consistent with a real dark matter signal. So we placed constraints on the 3 different models that we considered. And so in particular, we have constraints on scalars. So this is a constraint on the coupling of the dilaton to other photons or electrons, that's shown on the y-axis, as a function of the dark matter mass and the frequency on the x-axis. And so the constraints that come from this search are basically solid lines, and the constraints that come from other searches are shown in dashed lines. And so while we don't beat the existing constraints from microscope and EGALT wash, but we do surpass the constraints that we've obtained from O3 and from GEO by about an order of magnitude at certain frequencies. For dark photons, the situation is better with respect to the other experiments. So we're actually able to, for a good portion of the parameter space, beat these existing constraints by about an order of magnitude or 2. And again, here, what's the constraint that's shown is the dark photon to baryon coupling on the y-axis as a function of the mass of the dark matter particle on the x-axis. And so you see here again the three methods that we've used in the solid colors and the existing experiments in the dashed lines. And so yeah, the one thing to remark here is that the cross-correlation limits are actually a bit weaker because of this finite light travel time effect. That the way that the cross-correlation works is that you pay a penalty because the detectors are not co-located and co-aligned, and you pay an even bigger penalty for this finite light travel time effect because the overlap reduction function is smaller compared to the just the differential strain that results from the fact that the mirrors are in different positions with respect to the incoming fields. So that's a bit technical, but just to say that these limits in general do beat the existing ones. And for tensors, the association is even better because it's very hard for these experiments that look for dark matter to actually probe tensor couplings, because EOT wash or these fifth force experiments, they kind of focus on they build materials and they look for if the acceleration is different in the present for different materials as a way of probing the fifth force. But they're not as sensitive to tensor bosons, while gravitational wave interferometers are quite sensitive to the tensor perturbations, because that's again what they were designed for. And so you can see here, this plot is a constraint on the IUCAA coupling on the y-axis versus the mass on the x-axis. And our constraints beats the fifth force ones by about 5 orders of magnitude, which is pretty exciting. And so I'll just talk about some prospects in the minute that I have left. So what we can do with this kind of work now is essentially we leverage existing methods and we leverage existing detectors to say something about dark matter. And as detectors improve, we will get better limits. But of course, there's no minimum coupling that we can at least write down. So we just have to keep going and hope that we find something. But the fact is that we can use these interferometers almost as a model independent probe of dark matter, because we don't actually care about what model of dark matter that exists when we do the search. We just look for a differential strain at every frequency. And we don't care whether it's coming from a dark photon or a dilaton or whatever. We just interpret the results, or null results, as coming from one of those few models. But then that begs the question, if we see something, can we really distinguish anything? And the answer is not right now, but we hope to be able to in the future. And yeah, just, can we think of ways to design future instruments to actually look for dark matter as well as gravitational waves? That would be something that we can maybe discuss in the discussion session, because if you can use different materials, for example, you can improve the sensitivity towards coupling of dark photons and baryon lepton number. So yeah, I'll just end here. I'm out of time and leave my conclusions here. So I'm happy to take questions. Thank you for listening.
Very interesting work. Are there potential gravitational wave sources that would produce signals like this, like accreting neutron stars, for example? What you're looking for is like a correlated stochastic narrowband noise, right?
Yeah.
And
so, I mean, I think it's possible, but I think the kind of thing that would save us to be able to distinguish from that is that really when you try to confirm if the candidate is real or not, you have to, in the continuous wave case, you increase the coherence time as much as you can to the observation time, and you expect the SNR to go up. But in this case, you expect the SNR to go down, because the coherence time, once you exceed the coherence time of the signal, then you lose SNR, like you can see in this plot. So this is the best way that we can have to at least say it's not the astrophysical neutron star source.
Yeah, so these signals can be transient, right? Or they not last long enough.
No, they're forever lasting.
Therefore, okay, with the same spectral and amplitude characteristics.
Yeah. So I mean, like at any given amount of time, you would, if you take a Fourier transform of the data, you'll see this kind of spectrum. But the amplitude of the signal is, I mean, it's always there, right? Like I don't think it's not really changing.
What is the frequency at which you see the signal, which comes from the interaction between dark photon and
just the mass control of the
when
frequency.
you did searches, you swept across the frequency range?
Yes.
Or? Okay.
Every hertz, yeah.
In the similar lines, that because what I was thinking was that maybe the scalar dark matter and vector boson one can occur only when you encounter a stream of dark matter, and maybe the tensor one, since you're saying it's a fifth force, it would always remain. So is I'm right in my understanding, or you're saying that all these three things would simultaneously be there all time in our detectors, the scalar, vector, and the tensor?
Well, I mean, if you believe that dark matter is multi-particle, then I guess they'd all be present. But I think the assumption is that they're all independent. So if one is there, the others are not there.
Okay. Also, I mean that like only when you get when our Earth is passing through a stream of dark matter particle, only that time we will see this, or will it always be there?
You mean this kind of?
Yeah, yeah.
No, I mean even for the tensor dark matter, I mean the dark matter is always there, whatever kind of, no matter what the spin is, and so it's still flowing through us, even though it's tensor. The only thing that's changing is the interaction. Is the interaction IUCAA? Is it through electrons or dark photon or with protons? So you always see this, no matter what the particle is.
Okay, yeah, thanks.
And thank Andrew once again.